Okay, so today we're going to talk about Lewis structures that have expanded octets. So it turns out that the octet rule, while we've been treating it as a hard and fast rule, is really only a true upper limit when you're dealing with second row atoms, carbon, nitrogen, oxygen, fluorine for the most part. When you are looking at heavier atoms in the third row and below, these guys can actually expand their octets and have more than just those those 4 pairs of electrons. They can have actually up to, in some cases, 7 pairs of electrons, although usually we don't see more than 6 pairs of electrons around the central atom in a Lewis structure. The reason they can do this is because they have empty d orbitals in their valence shells. Remember, if we're talking about sulfur, when we write the electron configuration of sulfur, it's going to be neon and then 3s2, 3p4. So there's no d electrons there, but we're in the n equals 3 shell, which has empty d orbitals. And so those d orbitals can actually work with the occupied valence orbitals and allow for the presence of more than 4 pairs of electrons. When you're in row 2, you only have the 2s and the 2p, so there's really only room for 8 electrons ever. So that's why the octet rule is hard and fast. Okay, so let's see how this works. We can imagine drawing the Lewis structure for sulfur hexafluoride. Okay, well right away we're like, okay, this is going to be different. Sulfur is clearly the least electronegative element because everything's less electronegative than fluorine, so we're going to put sulfur in the center. And then if you were going to go on, what are you going to do other than connect each fluorine to it with a single bond? Fluorine only has 1 open valence, right? It's got 7 valence electrons. So if you try to connect fluorine in any other way, you're not going to be able to do it. If you start trying to chain the fluorine atoms, you're not going to have room for all the electrons that you need to put into the structure. Okay? So I really encourage you to try and see if you can draw the structure for sulfur hexafluoride without putting 6 bonds around the central carbon. You'll find that there's just no way to do it. And so that means there's only one thing that's possible, which is to put 6 single bonds around the central sulfur atom. And so clearly it has to have more than an octet, right? You have 2, 4, 6, 8, 10, 12 electrons around the central atom. Okay, so that's really it. So the rules for drawing Lewis structures are basically the same. You still put the least electronegative atom in the center. Okay, you're still trying to close open valences. You're still trying to, basically satisfy the need for those electrons to have at least an octet, for those atoms to have at least an octet around them. But if you have to, you're allowed to put more than 4 pairs of electrons around an atom if it's in the third row or below. So I want you guys to pause the video and try to draw the structure for SF4 and see if you can figure out what to do. You need to go through all the step-by-step process of, we already know sulfur is going to be the central atom. So go ahead, put the fluorines around it, start filling in the electrons, do all your accounting, and see if you can figure out what you need to do with that structure. Okay, so you probably came up with something like this pretty quickly. Okay, so you've got a sulfur in the middle, and you've got 4 single bonds to fluorine atoms. Each of those fluorines needs to have 3 more electrons around it, 3 more electron pairs around it, 3 lone pairs of electrons. And this is fine, except if you went through your accounting properly, you needed to add up the valence electrons. So let's see what happens when we do that. Each fluorine is going to bring 7 valence electrons, so that's 28 for the 4 fluorines. And then sulfur is going to bring 6 valence electrons, so 28 plus 6 is 34. Okay, so, well, let's count up what we have. We have basically 4 octets, so that's 32. We're missing a pair of electrons. So in order to make this a correct Lewis structure, it has to have the right number of valence electrons. So we've got to put another pair of electrons in somewhere. There's only one place they can go. So if you got this far, the only decision you can make is to put that lone pair on the central atom, and that's right. So that now is a complete and correct Lewis structure for sulfur tetrafluoride, SF4. Okay. There's another thing here that we need to take into account, which is that since we don't have the octet rule as a strict rule anymore, finding the best Lewis structure can be trickier when more than one is possible, right? It's not just going to be a question of, oh, well, we don't have an octet, so we can move lone pairs around, make double bonds, whatever, in order to get an octet around every atom. Now we are going to have multiple cases where we can have octets, and only one of them is really going to be the right structure. So how can we tell which one is correct? So let's get right into an example and consider drawing the Lewis structure for the phosphate ion, PO4 3-. So real quickly, you should be able to identify phosphorus is the least electronegative atom. You put it in the center, and then we're going to have to connect the 4 oxygen atoms to it with single bonds. Okay, great. Now when you go ahead, the next step in the process is that we should figure out how many electrons we need to be considering, how many valence electrons need to be in the structure. Well, each oxygen brings 6, so that's 24. Phosphorus brings 5. And then there's 3 minus charges on the phosphate ion, so that's another 8. So 24 and 8 is 32. Okay, so I've got 4 atoms. 32 is 4 octets. So real quickly, you can draw this structure, and it looks pretty good, right? All right, let's take a look. Every atom has an octet, so we're taught that's important. Every oxygen, basically is looking pretty good. We've got all of our electrons in there. Is this the final answer? And there's an additional consideration here. If you remember from the last video, we have the concept of formal charge. So now, even though we're not really considering resonance at this point, this kind of is a resonance structure for phosphate ion, because all that's left that we would have to be able to do is change the positions of double bonds and lone pairs. So let's see what the formal charges tell us about this structure. If we look at the phosphorus atom, phosphorus right now, it should have 5 valence electrons, and there are 4 single bonds around it. So that means phosphorus is going to have a formal charge of +1. There's no lone pairs, so we're going to subtract the number of single bonds from the number of valence electrons phosphorus normally has. And so you get a +1. Okay. And now if you look at the oxygen, it's a -1, right? You've got oxygen brings 6 valence electrons. You've got 6 valence electrons in these 3 lone pairs right here. All of those go with that oxygen, and then it gets 1 of the electrons from that single bond, so you end up with a -1 charge on that oxygen. And since all the other oxygens have the same arrangement, they're all going to have -1s too. So since our rule for formal charges is that they are supposed to be as close to 0 as possible, it seems pretty obvious there ought to be something we can do to get these formal charges closer to 0, at least in a couple cases, right? Because we have a +1 and a -1 in the same molecule, and they're right next to each other. So take a minute and see if you can see what you need to do in order to minimize those formal charges. Get at least 2 more formal charges to 0. Okay, I imagine it should have been pretty easy for you to realize you can put a double bond. If you move one of these lone pairs in between the phosphorus and the oxygen to make a double bond, and now you recalculate the formal charges, you'll see that that one's 0, and that one's 0, right? We've got 5 bonded pairs around that phosphorus to go with the 5 valence electrons, so that's nice, that's 0. Oxygen now has just 2 lone pairs, so that's 4, and 2 bonded pairs, and gets 1 from each of those, so that's 2 more, so for 6 to go with its 6 valence electrons, so that's 0. And then the other 3 oxygens are unchanged, and they're all -1. Can we do any better? Well, no, because remember that we want them all to be as close to 0 as possible, but they have to add up to the overall charge on the ion. So in this case, 3 minus is the overall charge on the ion. We've got 3 minus 1s. Okay? We could change the position of those minus 1s if we put another double bond in here. For example, if we made this oxygen double bonded, the oxygen atom would go to 0 for its formal charge, but now the phosphorus would be minus 1. And you should take a minute and think about why that's worse than the structure that's shown on the screen. Why do we want the minus 1s to be on the oxygen and not on the phosphorus? If you remember from the last video, when you have multiple choices for where you could put a negative charge, you always want it to be on the most electronegative atom. And in this structure, oxygen is the most electronegative atom, so that's where we want our negative charges. Right? The way that we draw Lewis structures, the external atoms, generally speaking, are more electronegative than the central atoms, and so we're going to want negative formal charges to reside on external atoms, and we're going to want positive formal charges to reside on central atoms when we have to have them in a structure. In this case, we were able to get rid of our positive formal charge by moving an electron pair to make a double bond, and that's often the case. Okay? So, the key point here is that in order to find the best structure now, when we can use expanded octets, you can use formal charges to determine the best arrangement of bonds and lone pairs around the atoms. And of course, I didn't mention it, that's the whole point of this video. The reason that we could make another double bond to the phosphorus so that it has 5 bonded pairs around it is because it's a third row atom. And it can do the same thing sulfur did on the previous page, and it can take extra lone pairs around that central atom. It can expand its octet. Okay, you should go right now and do the discussion question for this to reinforce these concepts.